Good morning, folks. This is lecture 2 of week number 7. And what we have on the agenda today is discussing the concept of a revolute joint. And in doing so, I will go through an example where, of course, I will create a revolute joint, animate it, and generate the trace of it, and then put some laws of physics into it, and I'll do some plotting down here. Okay, let's not worry about the details here. So the objective is to create a revolute joint, and let me remind you that a general three-dimensional rigid body has 6 degrees of freedom that are listed here: 3 translation and 3 rotations. When we are restraining some of the motions to create a mechanism like that, as you can see, or a joint like that, you basically have only 1 degree of freedom, and that is the rotation about this axis. That is what is called a revolute joint. For example, the hinge of a door. If you look at the door in your room, you see that the hinges are actually revolute. Now, in trying to show you how this thing works, I will look at a problem from chapter 3, which basically we have let's say a link of length 5 inches, as you can see there, and this is on a base, sitting on a base, and it revolves around that base at a given speed that's down here. Now, from elementary physics or elementary, actually, math, you can show that the position of let's say the tip of that let me see now. This slender rotating object is the coordinates x and y are given in terms of the radius. The radius means that the distance from the center of rotation all the way to the tip. That's what I mean by radius. And the speed, the angular speed of the arm. Okay, and if you differentiate, you get this, and you differentiate twice, you get essentially the same thing back as the original displacement. So the plot of for example, if you look at the x and y, the derivatives of x and y, or the components of the x and y velocity components, are given as sinusoid like that. Okay. So anyway, this is the way we're going to check, for example, to see if our answers are correct or not. All right, so let's go here, and I'm going to create something that looks like that. The only thing that I need to do is to make sure that the center, or the arm of this, what's the length of this link from the center all the way to the tip, is 5 inches. The actual shape doesn't matter. The radius of this corner doesn't matter. Okay, so let's go ahead and start with a product file. We start with product, and immediately I'm going to save it. Now notice that you're not in assembly design, and the only way to get there, you go to start, mechanical design, and assembly design. This is where you want to be, not in this environment. This is the DMU kinematic environment. Okay, so this is the only way, double gears right there. And then I'm going to save it immediately. File, save management. I'm going to save this thing in this folder. Let's see now, in right here. How about right there? Okay, let's do it right there. I'm going to call this thing revolute joint. Revolute joint problem. Okay, good. So everything is going to go there. First thing I'm going to do is to create that arm. Okay, so insert a new part in there, and I'm going to call it arm. Right click properties. Where is that? properties. The part name is arm, and the instance name is arm to make my job easier for debugging purposes if needed. And I'm going to make the arm. Double click on that arm. On that vertical plane, on that horizontal plane, I will sketch something that looks like that thing that you see there. For example, let's see now, go here. Oops. Yeah, turn it around all the way there. Okay, so let's look at this thing from the front view. All right, good. Now, the only thing that I have to do is to make sure that the distance from this point all the way to that tip is 5 inches. Now, it is true that these don't look tangent. If you want, you can make it tangent, but it's not a big deal. So that line control this. Those are totally irrelevant, but why not? Why don't we make it tangent? Okay, it looks like it was tangent. And the distance from here to there, 5 inches. 5 inches. Good. Exit. That dimension is totally irrelevant in the problem that we're doing. So exit. And let me pad this thing by, again, that size is also irrelevant. I'll make it 0.25 so that it looks nicer. Okay, like that. Then I'm going to insert the base. So insert a new part. Always say no, or I always say no. Right click properties. Part name is base. And this is the instance name, also base. All right, so let's go make it. Double click. All it is a cylinder basically. On purpose, okay, on purpose, I'm going to select this plane, and on purpose, I'm going to draw it right there. This is going to be the base. Okay. Now remember, this arm has to be on that base, but we'll do that. So exit, and we pad it. There we are. Okay, what do I change the color of this also? Properties, graphics. Yeah, I'll change it to yellow. Just for fun. Okay, all the way to the top, to go to the assembly design right there. See that? Double gears, and you click on the floppy. So these two parts are going to be saved in that same folder. Now we're going to assemble it. First, I'm going to anchor this piece because this is the stationary part. So I'm going to anchor. Now remember, these are assembly constraints that we are putting there. They're not joints, but we're going to use the magic wand later on to convert these assembly constraints into appropriate joints. Okay, now I want to place this guy on that face. So coincidence between that face and the bottom of that. Actually, it doesn't matter. You can choose the top, but then you have to flip these arrows if necessary. And if you update, you'll see that it actually shifts it up. You can see that right now. If you update it, that arm shifts up. And I want a coincidence between that axis and this axis. So basically, I have that mechanism that you saw in the slides. And let's save everything. So now we're going to go to digital markup right here. Digital markup, DMU kinematics. Notice that I end up where I was initially, right there. See that the pointy hat, which is that. Okay, good. Now there is this toolbar here called DMU kinematics. You can't miss it. There is the two gears, which means assembly design constraint, and the magic wand. So magically try to generate joints from the assembly constraint. So you click on it. It's going to say it's a new mechanism. Yes. What would you like to call it? I'll call it mechanism number 1. This is just the name. Give it any name that you want and auto create. Notice that unresolved pairs are 1 out of 1. Auto create, it shows you 0 out of 1. So what exactly happened here? Let's go check. This last branch was created for you, application. It says mechanisms. There is a mechanism number 1. Remember, I decided to keep that name, and the degree of freedom 1. Now notice what we did is to say that the surfaces of these two match, and the axis of these two cylindrical surfaces also match. That means this can only revolve about that axis and stay flush with it. What that means is that we have a revolute joint. And the one that you see here means the single degree of freedom that is the angular position of this arm. In fact, you open it up, you see joints, and you see a revolute joints. Okay. Now, in order to animate these things, make cartoons or make things move, this has to be 0. And how are we going to do that? We're going to double click on this revolute. This thing opens up. And by the way, notice that because I changed the instance names, it says exactly what the constraints are between the base and the arm, between the base and the arm. Now, there is an angle-driven box here. This is an angle-driven joint. So if you click it, notice that there is a blue arrow here. See that? The blue arrow, see that? If you want it to go in the clockwise direction, you just click on it and it goes the other way around. In this particular problem, it doesn't matter. And this can go between 0 and 360, minus 360 and 360. But because I want to animate it to go in only one direction, I don't really need this to be minus 360. I'll change it to 0 to 360. You say, okay? And your best friend shows up. Mechanism can be simulated. You say, okay. And now we're going to go, for now, we're done with this. And I want to remind you also, all the joints that you want can be manually created. In fact, after I do this problem, I come back and repeat it by creating the joint manually myself. The very first one says revolute joint. The second one says prismatic joint. That's the one that we did 2 days ago on Tuesday, lecture 1, week 7. Okay? But anyway, these are the ones we're going to do in the next few weeks of the course, gradually. Now notice that here in the DMU command where the magic wand was, etc., you have this first icon, which is actually made of 2 icons buried inside of it. One of them says simulation with command, the other one is simulation with loss. I need to use this when I actually put some physics into the problem. But this is just a cartoon type of thing. You click on it, and you're in charge. There's a single degree of freedom, and by dragging this thing, this arm will go from 0 to 360 degrees in the direction that you want, in this direction. Okay. So this is simulation with command. The problem is that as soon as you say close, there's no trace of it here. By the way, this is immediate, but if you say on request, you can type any number that you want here, for example, 90, and then say play. So it goes between 0 and 90. Okay, so you're basically restricting the motion there 0 to 90. Okay, but anyway, that's not what I want. I just reset it and then close that. Now, well, first of all, let's save this before we forget. Now, in order to have a record of all this stuff here, okay, we're going to use the simulation. This is a very important toolbar. We already used the magic wand. We already used the simulation with command. This is the other important toolbar. The very first one says simulation. A couple of things here, and notice that before I do that, I made that angle-driven join, and that is right here. You can see that command. This is the command. If I double-click on it, it tells you that this is the command that I issued by making it angle-driven. A fixed part was the base that was inherited from the assembly constraints. Okay, and there is no physics, no laws. You can see that. Okay, good. So to create a cartoonish type thing, you click on the simulation. It says, why don't you create a simulation? So I drag this thing all the way to the end, insert, rewind, and you change this thing, not the speed of 1, because if you do a speed of 1, it just jumps all the way to the end. Jumps all the way to the end, you can't see anything. So reset, change the speed here to something else, and now play it. Oh, you know what? I think I forgot to insert that. Let me start over. Cancel. Okay, try it again. Good. Drag this thing all the way to the end. Don't forget to insert. Insert right there. I forgot to do that last time. If you keep it as 1, all that thing does is that if I reset it, what is that? Reset this, it jumps. But if I change the speed, oh, I just noticed that this is actually the second one. Let me see for a second. There's two things here, but that's okay. Let me we'll clean it up. Okay. This second one I'm going to delete. Okay. What do I mean by the second one I'm going to delete? Rewind this thing. You see this? Click on that arrow. This is the second one. Delete that. So there's only one of them. You play it, and there we are. I screwed up. Okay. Good. Reset. Oh, by the way, if you wanted this thing to be going continuously, you use this thing, arrows chasing each other, so it goes, keep going. 360, then again, and again. It's like, basically, it's a cartoon motion, no physics into this thing. If the arrows are going away from each other, like that, it goes forward, and when it reaches 360, it goes backward. Okay, right there, you can see that. Anyway, rewind, close. So a simulation has been created here, right there. Okay, now let's create a replay for that. In other words, let me go and open this up in the DMU generic animation. The second one on the left, it says replay, create a replay. And let's not use 1, speed of 1, because we can't see much. I'll use 0.02. The simulation has already been created. You need a simulation before you can create a replay. And just say, okay, let it finish. Good. Now, all you have to do is to see what you have done is double click on replay. One dialog box shows up. And if you want to play it continuously, make the arrows chase each other. This is the speed, and let it play. So we come back tomorrow. All you have to do is to double click on replay and do this. Now, there's another reason that we want to create this. We want to use this icon, and that is to generate animation file. Let me stop this, rewind, close. Let's do another one. This is another compile, but this time I'm going to say generate an animation file. I don't want to generate a replay. The speed, I'm going to change it to whatever I want. And the file name, let's see now, file name, I call this thing my first AVI or movie. I don't know, movie. Okay, good. Say save, give it time, say okay, give it time until it creates the animation file, and we're going to check it out. Where would that be? It's going to be user, my name, etc. So this is done. Let's go check it. So I go to here. Where's user? Let's see. This PC. Wait a minute. Could it be here? I put it in a particular folder, but no. Let me see. Where is that thing? Desktop. Where would I find user here? This PC. Maybe desktop. You know what? I don't know where the user folder is. So what I'm going to do instead, what I'm going to do instead is this. Let me close that. Do another one. So another one. This time I'm going to file name. I'm going to put it on my desktop. How about that? Okay. It's already there, but I don't know how to get there. So that's terrible. Desktop. My video. Second video. Second movie. Second movie. Okay, so you say all right, don't use the speed of 1, and then just say okay. Good. So let me go to my desktop, and it's right there. Media player. Okay. Yep, this is the one that I just did. Okay. I lost the first one. I don't know where user directory is. So let's get rid of this. Go back here. So there's two reasons that you may want to use this icon. Compile. One is to create a replay. The other one is to create a video file. Now, in order to find a trace of a point, for example, I want to know what path does this point take. You first must to create a replay, must compile and create a replay. You have no choice. But I did it right there. So I go to this icon. It says trace. It says element to trace out is this point, for example. And I don't know, I'll make it fewer than 50. I'll make it 30-ish. And then it's going to be created as this, as a new, this trace is going to be created as trace 1, which is a new part. You say fine. There we are. So you're going to have to save this thing in that folder, file, save management. There's the trace that is just created. Save as. That folder, desktop, right? Desktop, and I called it Revolut joint, right? Revolut. Oh no, where was that? Maybe in documents. I put my stuff somewhere. Oh, problem two. No, I called it Revolut. Maybe Revolut, right there, right there. Okay, we put it in there. We say okay. You have to keep track of these for your final exam. You already know how to do it. All right. So now, if I want to bring the Revolut the trace in here, I say insert existing component in there. And what do I want to put in there? Is that trace trace that I created? It's right here. Trace one. Now I know where I put my first video. That's fine. There we are. And if you, in fact, if you play if you say replay, you see that it actually traverses that there. That's how you create traces. And I will ask you to create a trace on the final exam. Rewind, we say okay. So at this point, there is no physics behind any of this stuff. Now what I want to do is to say that the speed of this is 2 pi radians per second, or 360 degrees per second, or 1 hertz. Okay? So in order to do that, you need to go and create laws. In the knowledge toolbar, there is this thing f of x. You click on it. It gives you the entire database associated with these problems. When I say these problems, there was a product, and in it there were parts, etc. There were dimensions in the part. So I'm not interested in those. All I want is my mechanism. You click on it, there's only two things. There is time and the angle. Remember, this is an angle-driven joint. In other words, the position of that arm, which is the angle traverse, and time. Okay, so here's what you're going to do. You're going to click on this. This says that angle, add a formula. The left side is the angle associated with the arm. Equal to, don't type equal because the equal is already here. And whatever you write at the right side must come out to be in degrees, because the angle, my default units is degrees. So here's what I'm going to do. 360 DEG in 1 second, actually per second. Okay, there we are. So this means 360 degrees in 1 second. Not two underscores. I don't think you need a 1 here, but we'll just leave it like this, no problem. Times time. So I clicked on this time, and this is what's going to be typed here, but I double click on it, it's going to be typed there automatically. If there is a problem with the syntax, you're going to get an error message. If I say okay, notice that, by the way, the left side is angle, the right side is angle, because it's 360 degrees in 1 second, divided by second, times seconds, okay? Good, no error messages. We say, okay, so we now have a physics in this problem. And the physics is, we have specified the speed of that arm. Now, if this is bothering you, you can always hide it. You can always go and hide the trace. There we are. Okay, very good. All right. Now, a couple of things I noticed is that when I created this yellow piece, it was not at the 0, 0 position, okay? And therefore, when I plot X and Y later on, they don't quite look like this. They're shifted, but that's okay. That's okay. All right. Because I realized that this is not. I should have really created this at the global 000. When I do this lecture tomorrow, I will point out that it's better if you take this thing and don't put it there, put it at 000. That's okay. Now, let's go back to here to this DMU kinematics where the anchor is and the magic wand is, etc. Remember the simulation with laws right there. Simulation with laws. Simulation with laws. This was simulation with command. This is simulation with laws. You click on it, and incidentally, notice that I created my law. The physics is right here in the tree. You can see. Let me cancel that for a second. Right there, you can see that. It's right here. There is my law. If you want to change it, double click on it. You can go and change it. For example, if you want it to be 720 degrees in second, just change it, etc. You can do it from here, or you can click on f of x, and there is your formula that you type. Either way. Okay, let's go to simulation with laws. And this default is 10 seconds. I don't want 10 seconds. I want this thing to go 2 rounds. So I'm going to make it 2 seconds because the speed was 360 degrees in 1 second. So 2 seconds is going to be 2 rounds. Okay, you say okay. And the thing is that if you play this, you don't notice that there's any physics in it. Basically, it goes at a constant speed. You might say that, wow, this is exactly what I saw when I was doing it, no loss, okay? You're right, but the physics is there. And to convince you that the physics is there, we're going to plot a few things. For example, what I want to do is I want to plot the velocity of that tip as a function of time. Now notice that uh, this radius is 5 inches. The radius of the arm is 5 inches. So that's your little r, and omega, which is your angular speed, is 360 degrees per second, which means 2 pi in 1 second. So 5 times 2 pi. R times omega is going to give you the speed of this point. The speed of this point is going to be constant, and it's going to be 10 pi 10 pi inch per second, which means 31.4 inch per second, correct? If I don't get that as a constant value, something is wrong with my problem. So in order to do that, first thing you're going to do is you're going to create a sensor. Don't forget, DMU kinematics, we have already used the magic wand. We have already used the first icon, okay? We didn't have to do the third one because the third one, all of them were generated with the magic wand, okay? The only joint was generated with the magic wand. The ball rolling down a hill, speed and acceleration. You click on it, it says, okay, this is the name, fine. I can call this thing, how about calling it tip velocity? Okay, how about calling it tip velocity? Tip speed, how about that? Tip speed or tip of the arm, how about that? Tip of the arm, okay? A reference product is going to be that base. In other words, anything that we calculate with respect to that base, the base is stationary. Okay, and then we say the point is, for example, this point or that point, it really doesn't matter. I'll take this point. And we say, okay. So here we have created actually a speed acceleration sensor. Now we go to simulation with laws, where we were before. Activate sensor, and let's see the things that we want to plot. For example, I want to plot, right now I told you that I wanted to plot the speed as a function of time. So you go find, see, these are the position, X and Y position. These are X component of the velocity of this point, Y component of the velocity of this point, Z component, and this one which doesn't have any X, Y, Z in it is just the magnitude. That's what I want. Notice that when I clicked on this, this became a yes. Okay? Now, I don't need anything else. I'm just going to move this thing down. I'm just going to move it down. And I'm going to play this. Just give it time. Just give it time. There we are. Then you drag this thing up and you say graphic. It better be 31.4 and it is 31.4. You zoom in, zoom out so that I can see your scale. The units must be inch per second, speed, and this is second. Now, if I ask you to generate something like that on the test, you better save this. But the only way to save it is by print screen. You go start a Word document, either a Word document or I don't know, JPEG, Paint, whatever. Okay. Paste it. There we are. Save it, File, Save As. Where did we put that thing now? Okay. Okay, so it was Revolut right here. And say my generated speed versus time tip. Okay, say okay. Now, when it comes to marking your test, I can go to that folder. You see if I have the folder here. Was it documents? Revolut join. Oh yeah, right here. Right there. Oops. Where did I put it? Documents. It must be somewhere here. Okay, we're going to save it in the right spot. So this was terrible. Okay, so let's go back here. Oops. Do it again. Word document. Paste. Save as. Okay. Why don't I put it on my desktop? But remember, on the test, you have to put this thing in the proper folder, the same place that you're saving your parts and your product, etc., for that problem, and submit it. Okay? So I'm really sorry, but I don't know where that folder is. So I'm just going to put it on my desktop. Browse, desktop, my misplaced plot. Kill this, Go down here, let's go check it out. Make sure it's my misplaced plot, right there. I need to see this when it comes to marking your test. I need to see the scale, and you have to give me the plot that I'm asking for. Don't make your own plot and give it, please. Okay, so let's go back here. Let me close that. Suppose that I want to plot something else. Let me rewind this first of all. Suppose I want to plot, for example, X position versus time. So you go here, X vertex and Y vertex, okay? And say, move this, remember these things that you want to plot, they're generated here, right there, okay? You say, okay, play it. Play it. It's going to go twice, right? 2 seconds. Now these are going to be plots versus time. X position versus time, Y position versus time, and of course the one that I already did. Okay, so if you say graphics, there we are. This top one is your speed. This one, the X component of the velocity. This one is the Y, not the velocity, sorry. X component of the position, X of that tip, and this is Y of that tip. This green one is the Y of that tip. Now, again, if I ask you to give me this plot, make sure you zoom out so that all the units are observable here. You do a print screen, okay? So let's see, where's that print screen? You go to your Word document, which is, I believe, here, and add to that, boom, paste. Okay, let's keep that thing for now there. Now, suppose I wanted actually the plot of X versus Y. Now we know what's going to happen. X versus Y is going to be a circle. You know that, right? Suppose I want the plot of not versus time. These are versus time. Okay, the horizontal axis is time. But I want X versus Y. So I go and say options. Okay, option. See that? Instead of graphics, say option. Not versus time, customize. Okay. Now it looks like what we have done here, I don't have those things generated, so that's fine, no problem. Let me close that. Let me close that. Let me rewind this and play it again. What I should have done was also to clear my history, but I didn't. So that is not. I should have gone to history and then do it clear, but that's okay. No problem. We'll get there. Okay, let's see if these are generated here. Options, add. Okay, add. So what do we want here? The stuff that we generated was, see that? Customize, add. We want X versus Y, X versus Y. So let's get X vertex we asked for it, remember? And Y vertex we asked for it. You say okay. Something generated, curve 1. And you say okay. Yeah. Good. And now graph it. There we are. Okay. So if you want to generate things versus time, no problem. if you want to generate something versus something else, first you must have requested both of those things. And once you requested both of those things, in other words, in that list, the things that you want are all saying yes, yes, yes. Then you go and say customize graph, add, and then you go and select what is it that you want. So here, if I ask you to generate this, again, you get it, you do a print screen, and then you go and add it to this home paste. So we have the first two and the third one, and these are the things that I asked. Please make sure you generate the things that I asked you to do for the final exam. Because if you give me all kinds of plots, you're going to lose a lot of marks. Okay? And I'm pretty sure you don't want to lose a lot of marks. Okay? Now, let me finish this thing very quickly. So let me save this thing. Save. Go here. We close that and rewind this thing and close it and close it and close it. Okay. Let me get my product back. So open or file. This is the product that I closed. That looks familiar to you. Now, I'm not going to use the magic wand. What I'm going to do is I'm going to say, create a Revolut join for me right there. See that? The application is already there. Okay? But there are no, okay, I'm going to delete this. Yeah, delete that. As a matter of fact, let's do the following. Okay, let me delete this entire mechanism. Here, start from here, delete this. Okay, the mechanism is all gone, right? Okay, so here's what you're going to do. No mechanism here. So first thing, we want to create our mechanism. I'm not going to use the magic wand. And notice that there is no constraints here, assembly constraint, including nothing is fixed. So when I try to create a Revolut join, it's going to come and say, hey, wait a minute. Well, let me put it this way. First of all, I want to anchor this guy. So I click on that. It says new mechanism, yes. Mechanism 1, yes. It says, okay, go and select the thing that you want to fix right there. Okay? And now I'm going to do Revolut join. Revolut join. Notice that here I have to go and select the constraints basically. It says line and line. So this line and that line, plane and plane, this plane and that plane. And say, okay, good. Degree of freedom 1, double click on it, angle driven, 0 to 360. Mechanism can be simulated, simulation with loss. Hallelujah. The moral of the story is that we use the magic wand to create our join, prismatic join in the chap on Tuesday and Revolut join today. But you didn't have to use this magic wand. You could have generated these things directly. Not all joins can be done with the magic wand. Okay. So basically, this takes care of the lecture today. We're going to be doing many of these in the next few weeks. Okay? I'm not going to put the law here because I already showed you how to do that. It's the same story. You want to create the law, you just go and create f of x, select f of x, click on mechanism, and just follow the same procedure. It's the same thing. Good luck. And we don't remember, university is closed on Friday, June 30th, and in view of the Canada Day on Saturday, July 1st. So happy Canada Day. All right. Have a good long weekend.